So let's go through this checkpoint 16, the nuclear physics. So we have this barium 137 nucleus in the excited state undergoing your gamma decay to return to the ground state. So we are given that the energy of the gamma photon to be 1.06 times 10 negative 13, and the mass of the barium 137 nucleus in the ground state to be as such. So what is the mass of the barium 137 in the excited state? Okay, so first thing, we can actually eliminate two answers already. So because why? Because apparently excited state means your energy is high. If energy is high, of course your mass will be higher. So my answer cannot be less than the 136.9058 U. So A and B is out already. Okay, so let's see how do we actually calculate the mass of the thing in the excited state. Right? Okay, first thing first, we must consider a few things. So for example, at the start, let's just say the excited barium nucleus is not moving. Meaning that the energy that it possesses is the E equal to mc square. I put the asterisk is to denote that it's excited. Then after that, it undergo your gamma decay, right? So gamma decay, of course, let's just say gamma photon move to the right hand side, barium move to the left hand side. Okay, for the barium, the excited barium, it has two energy. The first one is what we call the rest mass energy. So you can see I calculate the rest mass energy to be as such. Then after that, it also have a kinetic energy, because apparently, right, we must conserve the momentum, because at the start, right, the excited barium has no momentum. So after that, the gamma photon move to the right hand side. Definitely your barium must move to the left hand side. So if you look at the gamma photon has an energy to be 1.06 times 10 negative 13 joules. And I want to determine what is the momentum of the gamma photon. I simply just determine the wavelength first using the E equal to hc lambda, right? Then after that, you use your d Broglie wavelength, P equal to h over lambda. So I calculated the momentum of the gamma photon is as such. Means that my de-excited barium nucleus, right, must have the same momentum, because they will cancel each other, right? Such that the overall momentum is equal to 0. Okay, so with this, I can actually calculate what is the kinetic energy of your barium, the excited barium, using the formula that we learned in quantum, right? P squared over 2m. So you do the substitution, you will get something like 2.7479 times 10 negative 19. So these are some of the energies for us to calculate. And of course, you might see that the kinetic energy of the barium, right, is a few orders lesser than the energy of the photon. So to be frank, you don't need to consider the kinetic energy of the barium. Okay, but let's just say I consider. So let's determine what is the idea of the energy release in the decay, right? So how do I actually determine what is the energy release? Very simple. You simply just use the rest mass energy of your excited barium minus of the rest mass energy of your de-excited barium. So it's like m star c square minus mc square. So this will give you the energy release. So this part is the energy release. Okay, so this energy release is in the form of something, right? So it's in the form of the kinetic energy of the de-excited barium and the energy of the photon or gamma photon. Just put like that. Okay, so I just do my calculation again. So of course I'll get m star c square, which is the rest mass energy of your barium to be as such. So this one is in terms of joules. Okay, then I want to determine what is the m star, meaning what is the mass of the excited barium nucleus. You divide by c square, you'll get something like this. Okay, so how do I do the conversion from kg to unified atomic mass, right? You simply just divide by 1.66 times 10 negative 27. So you will get this. So the answer is still C. So this is after we do all the consideration of the kinetic energy, etc., etc. So to be frank, for this, right, the kinetic energy of the de-excited barium actually is don't need to care, because it's too small already as compared to the energy of the photon. So that is why for checkpoint 16 the answer is C.